All right, we good? Excellent. Okay, so we're looking at page 98, number 10, which says, how much tension must a rope withstand if it is used to accelerate a 1,200 kilogram car vertically upward at 0.80 meters per second squared? So we have a car. Here is my wonderful drawing of a car. And it's being pulled upward by a rope.
From the bridge?
Presumably. Hopefully not. I imagine not by hand. The mass of the car is 1,200 kilograms. And the acceleration of the whole system is 0.80 meters per second squared.
Oh.
And the question is, how much tension must the rope be able to withstand in order to do this?
You gotta
Okay.
factor gravity.
Got to factor gravity in. Perfect. What's already happening with the car is gravity is attempting to accelerate the car downward at 9.80 meters per second squared, correct?
Mm-hmm.
So just for the rope to keep the car perfectly still, the rope would have to be withstanding, well, I'm going to switch now. This is gravity. This is an acceleration vector, right? That's negative. I'm going to switch to a force vector. Just to hold everything still, the force would have to be mass times acceleration. It would have to be the 1,200 kilograms of the car times 9.80 meters per second, just for the rope to handle the car's weight, which is its mass times gravity. Any questions on that idea? So this represents what the rope would have to do just to fight this downward acceleration vector. Does that make sense?
Yes, sir.
Danny, can you see? You can move behind Jake. Okay. In addition to that, what else would we like this rope to do besides just fight gravity?
Hold up.
Hold the car.
Pull the car up. Not only that, but with an acceleration, not even at a constant speed.
Right. So you gotta add 0.80 meters per second squared to the 9.80.
Very good. Take my zip. Now, this is a force vector. I can only add a force vector to another force vector. So my additional force vector, we'll call this F sub 1, this F sub 2, is the mass of the car, which hasn't changed. The kidnapped victim has not suddenly jumped out of the trunk while this is happening. We also need an additional 0.80 meters per second squared of acceleration. Quick conceptual question. Well, first, any questions on this? The rope has to handle this force just due to gravity, this force due to wanting to accelerate it. Quick conceptual question. Forgetting for a moment that you would have to accelerate to get the car moving. Once you get the car moving at a constant speed, how much force would be required to keep it moving at a constant speed? This much, or some other amount? You want to keep the car moving at a constant speed.
The second.
Yeah.
Which one?
Both.
To keep the car moving at a constant speed, the rope only has to handle this. If you're pulling up an object and it's not accelerating, then all the rope is doing is fighting gravity. Your muscles are doing other things. The winch is doing other things. There's power and work and all sorts of things involved. But it's once it gets moving, if the rope doesn't snap when you start to pull something, which is the initial acceleration, it won't snap when you get it moving at a constant speed. Yes, Jake?
How is it that over time anything like under tension snaps?
If it hangs there long enough, you mean. Now you're talking wear, tear, and you're getting, that's actually a very good materials engineering question. And for now, just to get the concepts down, we have to talk about magical ropes that do not age. But,
Or magical chains.
or magical chains, whichever, yeah. Chains do rust, ropes do wear down. Cohesion starts breaking down
Nothing is
at every
permanent.
level. Nothing's permanent. Entropy wins. But the for our purposes of our much shorter term exercise. Yes, if this rope has already lifted 50,000 cars over the last 20 years, and lots of dust has gotten in and grime has gotten in, it
Then
could
it's a
snap
different
it
problem.
could snap if you look at it wrong. But that's a totally different situation than this. But the problem says the car is accelerating at this moment, so the rope has to be able to handle both of these. How much tension is this? What will F1 plus F2 equal? They'll equal 1,200 kilograms times 0.80 meters per second squared plus 9.80 meters per second squared. And how many newtons is that? Who's got the answer or a calculator?
12,720.
12,720 newtons, which are kilograms times meters per second squared. And they are a unit of force, not mass or acceleration. They're a unit of weight, which is a force. Any questions on number 10? Going once, going twice. We're good? Okay. I'm going to stick to this board today, so I'll just erase this one. And now number 9. Remy, you asked me if your answer was right. Was your answer right?
I think I read it's like the significant figure, but yeah, that's like the same process that I did.
Did you get that order of magnitude?
But I did the 1,200 kilograms times 1.8 plus 9.8.
Excellent. Okay. All right, so 9. A baseball. Baseball has a mass of 0.140 kilograms. This baseball has a mass of 1.40 kilograms.
0.14.
0.140 kilograms, thank you. And it is traveling at, as initial velocity of 35.0 meters per second when it strikes the catcher's mitt. Now the catcher's mitt gets the ball down to a final velocity of 0 meters per second, and it takes 11.0 centimeters to do so, which is 0.0110 meters, correct? No, centimeters are only 100. I only need 2 decimal jumps. So that's 0.110 meters. Is that the correct given information? Did I convert that correctly? Yes,
Yeah.
no, maybe
Yeah.
so. Silence implies consent.
Yes, sir.
Okay, so the ball hits the glove at 35 meters per second, and then takes 11 centimeters to bring it to a stop. So what we don't know right now is the actual acceleration. We need to find that. Okay? They did not give us the acceleration, so if you just plugged 35 or 0.110 or 11 in somewhere, couldn't get the right answer here. How much acceleration was this? Well, I was given velocity and a distance, so I need to go back to v squared equals v initial squared plus 2a x minus x initial. And my final velocity is 0 meters per second squared. My initial velocity is 35 meters per second, whole thing squared. I'm looking for the acceleration. And in that time, I covered 0.110 meters. How did I do it plugging everything in? So far, so good?
Yeah, all good.
All right, to solve this for my acceleration, I get negative 35 meters per second squared equals 2 times acceleration times 0.110 meters. And then my acceleration is going to equal negative 35 meters. Don't want to put that in the wrong place. meters per second squared over 2 times 0.110 meters. What is 35 times 35?
1,225.
1,225 meters squared over second squared over 0.220 meters. That meters will cancel with that. I will get an acceleration. I'm expecting this to get about 5 times larger because I'm dividing it by a decimal close to 1/5. Woo, so I'm looking at 6,000-ish.
You're looking at 5,568.
5,500 and which?
68.
68 meters per second squared. Negative.
Yeah.
So that's about, let's see, gravity rounds to 10 meters per second squared. So that is about 550 times more of an acceleration than gravity. Every time you stop a baseball. It's a lot of an acceleration. But it's not a lot of mass. The question was, what was the force required, right?
Right.
Okay, so force is mass times acceleration. We'll keep the negative because it is a decelerating force we're talking about. 0.140 kilograms times negative 5,568 meters per second squared gets me negative how many newtons?
Negative 779.52 newtons.
779.52 newtons. And I think this problem was only 2 significant figures or 3. This problem was 3 significant figures. So, even so, that's negative 780 newtons. Which is really just, it's about what somebody who, that's the same amount of force as someone who weighs about 170 pounds? No, 190 pounds, somewhere in that range. So less than 200 pounds. But does catching a baseball, even one thrown really hard, feel the same as holding someone up who weighs 200 pounds with one arm?
No.
No. Forces can feel very different depending on
Yeah. Most definitely.
how they work and which direction they're coming in
Most definitely.
and how quickly they go away. That gets into things like power and kinetic energy and other things. Any questions on number 9? Nope.
You should check the answer though, just to make sure.
In the back?
Yeah.
I'll let you do that. I feel good about it. I want to do one of your homework problems from 2 nights ahead that I assigned actually in class because it's a clever one. I want to see if you can figure it out. If you take too long to figure it out or get too crazy about it, I may have to stop the tape and let you think about it and put it back in when you get the answer. But, excellent. Tyler says we're right. Okay, let me take a look at it in the book. Okay, we're going to do number 14. So this is a new example. You can put this in as new notes. And when you see it on the homework later in the week, we'll have already done it.